So hello everyone, welcome again. Uh, so in the last bit of lectures, we have been discussing about the Drude's model. We found out the conductivity and hence also the resistivity from it. We had a form of the conductivity. It was first we started with the DC electrical conductivity and then we went on to learn about the AC electrical conductivity. We also learned about the Hall effect and how the phenomenon of Hall effect was employed even today to detect an unknown magnetic field. And then we went on to learn about the your thermal conductivity of a material. Alright. So we'll stop in the last lecture by deriving the thermal conductivity for a material. So now in this lecture, we will be transitioning into the quantum theory of solids. How the earlier things we were studying were all based on the classical picture, and I gave you a flavor of how using the quantum theory, in actuality the results deviate from the classical one. So in this lecture, we will be studying about the Sommerfeld's theory of free electrons in a metal. Let's check if it's recording or not. Yeah. So the electron was discovered by J. Thomson. People at that time had an idea that electrons are not classical, but they behave as quantum particles. They do not act like they are hearts, billiard ball like spheres. So they're no longer classical particles, but people realized that it was quantum in nature. Electron is a quantum mechanical particle. So Sommerfeld came up with the theory that the electrons needed in a metal or a solid needed to be treated quantum mechanically, and it is known as the Sommerfeld's theory of free electrons. So he contributed to the field in various ways. So A.W.J. Thomson, Sommerfeld prescribed the orbital quantum number, which is your L, this is given by L. Right. This give an idea of the shape of the orbitals. He also gave the spin quantum number. Which is your S. So he contributed to the field in various ways, and he also prescribed how you should treat the behavior of electrons in a solid, how they behave quantum mechanically, and he also modeled the quantum picture, how electrons behave in a solid. So we have been learning about the Drude's model, and it relied on the Maxwellian-Boltzmann distribution of electrons in a solid. So he treated it classically. So in the Drude model, the distribution of the electrons, the distribution of the electrons follows a Maxwellian Boltzmann nature. So it was like this, in that the distribution, if of the velocity distribution or number distribution, what you might say, is like this. So draw a graph how it behaved. So it was so this is your f of p. Fine. So this is your Maxwell Boltzmann distribution. Now we know that electrons don't behave in that manner. So electrons are quantum particles. Electrons are quantum spin-half particles, and follow Fermi Dirac distribution. So they no longer follow the classical Maxwell-Boltzmann distribution, but they follow the Fermi-Dirac distribution, or they obey the Fermi-Dirac statistics. So the Fermi-Dirac distribution here is given by your Fermi-Dirac of epsilon minus mu. I'm going into these terms later. So this is 1 by 1 plus e raised to epsilon minus mu over kT. So this is your Fermi-Dirac distribution, where epsilon is the energy and mu is the chemical potential. We will get into these terms in the duration of this lecture. Chemical potential. So the electrons follow a Fermi-Dirac distribution. If you have to sketch it, so let us just sketch it. It looks like this. Say at t equals 0, this is your Fermi-Dirac distribution. At t equals 0, distribution is 1 up to a certain energy, goes down, and this is at t equals 0, and this is your 1. This is 0. So it stays constant with a value 1 up to a certain energy value and drops down to 0 after a certain energy value. So this is your energy, right? And this is your chemical potential, the point where the Fermi-Dirac distribution goes down to 0, the point up to which it stays 1 and fixed. So you can understand why it is 1 and 0 as a form of the limiting value. So you look at this distribution. This is your 1 over 1 plus e raised to epsilon minus mu over kVt. Put t equals 0 and epsilon is less than mu. Alright, then epsilon, the power raised to epsilon, there is negative infinity. So this will be 1 plus e raised to minus infinity because t is 0 there. So this will be 1 over 1, which is 1. All right. Put t equals 0 and epsilon is greater than mu. This implies in that case this will be 1 plus e raised to infinity. So this will be much greater than 1. So this will be, so the Fermi distribution, this is 1 when epsilon is less than mu, and this is 0 when epsilon is greater than mu of the potential. All right, to visualize this picture, let us go back to basic quantum mechanics where we learned about particle in a box. This is just to give you an example of how to visualize this distribution or the Fermi distribution picture. All right, so we are talking about a specific example. Fine. All right. So the example we're talking about, or we are going to get into, is particle confined in a infinite potential box of length L. All right. So the picture is like this. You have a box fine, and the particle is trapped somewhere in between. This is your fine. So what will help us is the Schrodinger equation. So the points are that this is a free particle, which implies there's no interacting, there's no potential inside, only kinetic energy. So no potential. All right. Now we use the Schrodinger equation. All right. And for simplicity, we are going to work in one dimension. Simpler by working in one dimension. Fine. So let us just write the Schrodinger equation, which is minus h bar squared by 2m d2 psi dx2 is equals to epsilon n psi n, where psi n is the wave function. All right. So psi n is the wave function, and epsilon n is the energy eigenvalue. All right. Solving this, we get the solution of psi n as a times sine n pi x over L. All right. The solution you're very familiar with is that for different n, it will have different number of nodes, and the wave functions will behave. The wave functions will behave like this. For n equals 1, this is, you don't have a node. N equals 1, there will be n minus 1 nodes. So for this, the wave function will be like this. All right. So let me just draw it properly. Right. This does not look good. So here the first solution will be like this. So it will be like, yeah, this is one. And the second solution will have a single node because it is for n equals 2 and 2 minus 1, there will be one node. So the primary requirement for this solution is that the wave function should go to 0. So this is for n equals 1 and this is for n equals 2. Alright. So the primary requirement is that the wave function should go to 0 at the boundary. So as you can see that at x equals 0 and L, psi n goes to 0. Alright. So now doing a double derivative of the wave function, you can easily calculate that epsilon n is h squared over 2m and n by n whole square. This is n squared y squared h squared over 2m n squared. This is the energy eigenvalue. So corresponding to different energies, there will be different levels. So if this is your picture, this is the first level, this is the second level, this is the third level, so on and so forth. All right, so this is your epsilon 1. Sorry, I should write color. So this is your epsilon 1, this is your epsilon 2, this is your epsilon 3, and this is your epsilon 4, and so it continue in that fashion. So now you have to put in electrons in those energy levels. The first concern will be how many electrons you can put in a single energy level. As electrons are fermions, there will be the Fermi-Dirac statistics, and as per Pauli's exclusion principle, you can put in 2 electrons in a single level, one with spin up and another with spin down. So following Pauli's exclusion principle, following Pauli's exclusion principle, one level, of course energy levels, one level can accommodate only 2 electrons. Spin half and spin up and spin down. So corresponding to each energy level, there will be filling up of electrons. So one up electron, one down electron, one up electron, one down electron, one up electron. So if you plot the Fermi-Dirac distribution side by side to it, so it will look like this. So this is your y-axis is tilted. This is your x-axis. This is your energy axis. This is your energy axis, and this is your Fermi-Dirac distribution. All right. So up to this energy level, let's say up to E4, the electrons in that level are fully filled. It is up to a saturation point. So the occupancy level up to this point will be 1, and this is fairly easy to see. So up to this level, let's say, so will be filled up to this level. All right, and beyond that, there will be no filling because there are no electrons available. So depending on the number of electrons you are going to fill the energy levels. So this point will be marked as mu. which I told you is the chemical potential. The maximum energy level up to which the electrons are fully filled, or electrons are fully filled in the energy levels. So, and most importantly, we're all talking about the t equals 0 case. So this is your t equals 0 case. All right. So now you can imagine that you're continuously building up the energy levels for the problem, which is a free particle in a box confined in an infinite potential box. So in that case, you're going to fill up the energy levels with spin up and spin down electrons, and depending on the level up to which electrons are filled, it is the Carmichael distribution will be 1, and beyond that it will be 0. So this is your, I should write it clearly that this is your 1. All right. So now with that picture in mind, what happens when T is not equal to 0? For a finite temperature, what happens? Let us see. So these are your levels. All right. These are your energy levels. Fine. Now, up to certain energy levels, you are filling up with electrons spin up, and spin down. Now, in these two levels, as there are thermal fluctuations, so one will move up to this level, skipping this level, and another will stay in this level. So you can understand that because of this extra energy which is supplied by the thermal fluctuations will enable the spins to traverse up to a higher energy level. So in that case, if you draw the T, this is your T not equal to 0. So if you draw the graph side by side, so if this is your distribution, so what follows is this is epsilon. So this is your y-axis, which is called the Fermi epsilon minus mu. So up to this point, it will be smeared out. It's because the levels are not filled up to its full capacity. All right, this is because the thermal energy is supplying the extra energy, which enables some of the spins to go up to a different or higher energy level. So in that case, the electrons, the Fermi distribution will follow a proper distribution for the T not equals 0 case. The proper distribution is nothing but what I'm trying to say is that there will be a distribution in the non-occupancy levels of the electrons. So earlier it was just a straight flat curve where up to the chemical potential mu it was 1 and beyond that it was 0. But in this case, as because the levels are not filled up to its full capacity, electrons are traversing from one level to a different energy level because of the thermal fluctuations. The distribution, the curve in that portion of the energy levels will be smeared out and it will not be a flat curve, constant curve. So the main difference from the classical picture to the quantum picture is that in Maxwell, let me just write it, in Maxwell Boltzmann picture, temperature governed the particle distribution. As you said, as you saw that as temperature increased, the distribution spread out. All right, but the area under the curve was unity and it was same. So the particle temperature governed the particle distribution. But for the Fermi, Dirac, writing is bizarre in this case. For the Fermi, Dirac distribution, Pauli's exclusion principle governs the occupancy. This is the main diversion. That in that case, temperature govern the particle distribution, but in this case, we have discrete energy levels, and Pauli's exclusion principle governs the occupancy. All right, and as you can understand, this is your familiar equipartition theorem. So half m v mean squared is equals to half kBT. So each degree of freedom supplied the half kBT of energy. So in this case, before going into deeper concepts, let us just clearly define what the chemical potential and the also one addition, what is the Fermi energy. So before that, if there are n number of electrons in the solid, so in be the total number of electrons in the solid, then n will be given by summation k, Fermi distribution epsilon k minus k. So k is the wave vector. What? Yeah, electrons. All right. So this has indices k. This k is the wave vector of the electron, and epsilon k is your h cut squared k squared over 2m, and the momentum is p equals h cut k. Okay, vector, because this is the wave vector. So summing over the Fermi distribution will give you the total number of electrons present in the solid. And because of spin degeneracy, because electrons spin half particles here, and the spin degeneracy is 2, which is spin up and spin up and spin down. For spin degeneracy, an extra 2 has to be added, because we can accommodate 2 electrons in a single energy level. Has to be included. So this goes into as twice for distribution summation over it. So mu, clearly defined mu, is the energy level. So highest energy level is the highest energy level up to which the electrons are filled. Alright. This was our picture that particles, electrons are trapped in a box of length L, and the energy levels are like this. Energy levels are like this. And your distribution side by side is like this. cross it like this. So this is your distribution. Notice. So let's say up to this level you have filled the levels with electrons. So it will be like it will be like it will be like so this is your this point is marked as mu. So and as the terminology goes, the chemical potential at T equals 0 is defined by the Fermi energy. Alright, so Fermi energy is defined as F is defined as mu at T equals 0. Alright, and the total number of electrons, let me just highlight it. Total number of electrons is given by this. Alright, so this is the summation of the Fermi distribution over all the wave vectors. Alright, and naturally that is over the all the energy levels. So with this picture, Sommerfeld proposed that proposed that electrons inside the solid, which is the model we are developing, the model he developed, is that it is a particle in a box, and particles are the electrons, and your box is the solid. Sommerfeld proposed that, electrons. Uh, check once more. Yeah, it's recording. So Sommerfeld proposed that electrons inside the solid are non-interacting, non-interacting among themselves, with ions in the solid. So, because not only there are electrons, there are also ions, the positive ion force. So they are also not interacting with the ion force. The ions in the solid or any kind of impurities. All right. So that was we have been working in the 1D case till now, but in a solid it's in 3 dimension. So let us assume a cube. All right. So this is a cube. Side L. Was writing like this. So this is your L. This also is your L. And this is also your. So you have to employ the sorting the equation in this case also. He said that the electrons are trapped inside this box, trapped with the potential, the infinite potential of potential well of this is translated into the picture that this potential well is a cubic box. All right. that they can't go outside this potential box but stays freely inside it. So they are confined by the potential box, and now it's a cubic box in 3 dimension. All right. So Schrödinger's equation for a free particle, we should write it. So minus h squared over 2m grand squared psi k is equals to k psi k. So this is your Schrödinger equation in 3 dimensions. Your Ek is h squared k squared over 2m. This is your energy of a free particle. Slowly we are shifting the quantum picture from the classical picture with the but Sommerfeld said is that treat the electrons inside the solid as free electrons and they are non-interacting. So the only way to visualize this picture is writing the Schrödinger equation for it and solving the equation. Where epsilon k, which is the energy of the free particle, is h squared k squared over 2m. Let this psi k also in special dimension, psi k x y z, your wave function of the particle enclosed in the box, and the box is of volume V equals L cubed. All right. So the particles are trapped inside this box and moving about freely inside this box. So we are looking for solutions to this Schrödinger equation. The simplest solution will be to have the psi k as plane wave solution. Psi k, you can automatically understand that the psi k which is our plane wave form satisfy this Schrödinger equation. Psi k x y z can be written as psi naught e raised to I k vector dot r vector. R vector is nothing but x I cap plus y j cap plus z. All right, and this is your plane wave solution. All right. So now to find this multiplicative factor psi naught in front of it, we have to just do the complex conjugate and multiply it. We normalize the wave function and do the integration. We multiply it with the complex conjugate of psi k and we integrate over the whole space. So normalizing psi integration psi k star psi k d cubed r, which is over to volume integral. This is 1, implying modulus of psi naught squared times v is 1, because d cubed r will be integrated to v, and your psi naught will be given by 1 over root v. So what you have is psi k is 1 over root v times e raised to I k dot r vector. Simple. So earlier for free particle in a box, we were considering that the wave function should go to 0 at the boundary of the box. All right. So we are considering that the wave function should go to 0 at the boundary of the box. But Sommerfeld took a detour and predicted that it's not necessary that you have to take the wave function to be 0 at the boundaries. He considered considered that the wave function needn't be 0 at the boundaries. Rather, what he assumed or he told that they should obey they should obey the periodic boundary condition. Periodic boundary condition. What does this mean? So this means that if you have, for simplicity I'm drawing in one dimension, if you have a wave function like this also, so this is also a permissible solution to this. The wave function has to obey the periodic boundary condition. What does this mean? This means that psi k of x is equals to psi k of x plus L. This is your periodic boundary condition. Alright, it's a periodic boundary condition. So you can imagine that if the had the electrons obeyed the condition that it has to go 0 at the boundaries of the box that it is roaming into. So in that case, the electrons will bounce back from the walls of the box or the container, which will give rise to standing wave solutions. So in this case, in that case, there will be no propagation of the wave vector that the electron possesses. So it will give a standing wave solution. So, but you need to have the solution that is propagating solution. So for that case, you have to adopt the periodic boundary condition. So now you are imposing the periodic boundary condition that brings about changes in the nature of the wave function. So psi x is your 1 over root v e raised to I k dot x. Let's for simplicity consider in one dimension, which is again equal to psi k x plus L, which is given by 1 over root v e raised to I k dot x vector plus over. So therefore e raised to I k dot x is equals to e raised to I k dot x plus L. So now e raised to I k dot L is 1. Is equals to e raised to I 2 n 1. Therefore, k vector or the k is equals to 2 n pi over L. And this is n equals 0, 1. So once you impose the periodic boundary condition, the wave function, the wave vector will have to be quantized. Alright. So this is your kx. Similarly, we'll see that in the other directions also, if you consider a three-dimensional box and the electrons are trapped in this three-dimensional box, it will also the periodic boundary condition imposition will also impose some restrictions on the wave vectors that you can choose. So in that case, the wave vectors are quantized. Alright. So for this class, let's just stop here, and in the coming classes, we will discuss more of this Sommerfeld model. So let's stop here. Thank you.